Welcome to ANSYS V15 training series, and this video training is for everyone who is related to your R&D engineering, R&D design, CA analyst, CA engineer, application engineer, engineering domain design, and various other domains like automotive, aerospace, consumer product. Typically, you cater to the product design and you want to validate your product's different aspects like cost. Maybe you want to optimize the size and shape. Maybe you need to understand the aspects like the critical conditions and the manufacturing and other different domain aspects like cracks or maybe the fluid flow or maybe the typical products failure and so on. So there are a bunch of different options is pretty difficult to discuss, but the finite element analysis, that is ANSYS, is basically your protocol or the domain or the software package which you can use, and like ANSYS various other tools are there, and that we'll also discuss in our coming session in brief. But primarily this is one of the popular, or you can say one of the pioneer in finite element analysis, which most of the industry they adopt and uses. And other than that, you can see in most of the universities also they use for the research fellowship, and in the PhD and MTech program also they use this particular program. Let us discuss about our typical course objective, and primarily we are focused here to look at the fundamental aspect. And here I want to just highlight here, and we are intended to understand this particular fundamentals here. And fundamentals means how to apply, why you are going to use it, and primarily the finite element analysis applications that also will be looking in depth. The finite element analysis, this you may be new to this particular concept, but what is that, that also will be discussing in brief this particular. And this particular course we have designed by keeping fundamentals too advanced. So you'll understand how the fundamentals and the advanced concept inside the computer-aided engineering that we have kept in mind. We have included industry standard projects to better understand the concept and how to apply while working, and we'll be able to understand more about the boundary conditions. Boundary conditions, typically what I mean, that I'll be discussing material selection, pre-processing like the modeling, assigning material and different other assumptions, and then we'll solve it, and typically that is the post-processing, and we'll validate that your result which you are computing is right. And these are primarily some of the course objective which we'll discuss. And I am Pramit Kumar Senapati, and I primarily consult and work closely with product design, and primarily my specialization is CAE, computer aided engineering, and more than 100 products I've consulted, and I was subject matter expert for that and online available. You can see under Smart Learning Technologies Private Limited, and you can check my profile in LinkedIn, this particular profile, and also you can socially connect with me through Facebook, and this is my particular URL, or you can say ID. And the agenda is here, what we are going to cover, who are our targeted audience, and what do they do. This also I'll be discussing, and the module highlight, whatever different modules we have covered, and that's particular highlight. And also we'll discuss the prerequisites. And here I'll showcase one sample course where we'll understand that the standard of our course quality, and we'll show one sample course, preview course, and then the deliverable. These all are agenda here. And you may be wondering who are our targeted audience, or maybe who can learn this. It's always important to understand, interpret, and decide why you learn and who can learn and how you are going to benefit and when you can learn this typical CAE package application program, and how can you take the benefit of that. And this particular important aspect I'm going to discover. And our target audience is very broad, and couple of filtration I have done, like application engineer, design engineer, CAD, design engineer, CAE, CAD engineer, CAE engineer, development engineer, R&D engineer, product design and development engineer, project team leader, GM design, CAD trainers, tool design engineers, auto domain engineers, aero domain designers, and product design engineers, the special purpose machine SPM design engineer, CA analyst, and consultants. They all are our targeted audience, and probably I have not included all, and some of the highlights here you can find who can benefit from this particular course. And what do they do? That is one of the important aspect. They basically develop, or you can say modify, existing products. This you can see this particular point. And also you can see the application CAD CAM CA concept for product design. They are also involved in that. And here you can see the analyze user needs and develop engineering solutions, and also analyze design configurations for product and recommend optimum solution, and also customize engineering applications to automate the process and analyze manufacturing process and recommend this appropriate process plan to optimize the operational efficiencies. And also the customized product lifecycle management system, that is basically typically starting from the concept till product in your market, end-to-end digital product design and all the modifications related to that, and create technical specification and test plan as well. And last but not the least, the create appropriate documentation to ensure the traceability, or you can track it from the concept to the retirement of the system or the obsolescence of the system and subsystems and all this involvement. So typically these are the job responsibilities, or what do they do after learning this particular solution. And primarily these are very common in case of all the CAD CAM CE package, and that you have to understand and how to implement. That is very, very important. And let me give you about the modules highlight. The versions which we'll be using is ANSYS V15. And these are the modules which we'll be discussing, and starting from the, what you say, the introduction and the basic solid modeling, advanced solid modeling, the finite element modeling's foundation and advanced concepts. This all will be discussing as well. And you can see the one of the important aspect is this, which I used to discuss very, very broadly, is solution and post processing. And we'll look into some of the projects in static analysis, or you can say structural analysis, this, and advanced structural analysis, dynamic and nonlinear also will be covering, dynamic as well as this nonlinear. And we'll look at advanced structural analysis, this project, and we'll look into thermal analysis as well. And finally we'll talk about the generating the reports and how to customize that and get it documented, and then you can finally produce that. for your clients or maybe for reference or for any purpose. So let me brief about prerequisites, and you may be wondering, so what are different prerequisites? So this is very simple, straightforward. The CA is all about saving big prototype investment, and the best way to test your would-be product in a non-destructive way. This is very important. So non-destructive way. So non-destructive is something which primarily you talk about without having a particular test protocol. So you don't do testing, physically lab testing, and directly you save your money and your investment and mathematical accuracy, and in a proven way, that is the finite element analysis that you'll be using to better understand this whole process. So you need to understand that you need to have the prerequisite. So what is that? So that you have to understand, the prerequisite is all about interpreting mathematically and understand the assumptions, how you can simplify a particular project, and then mathematically you can get a idealized model or simulating model, or you can say the simplified model. And there you need lots of analytical abilities like your strength of material understanding. You need to know the strength of material, the machine design, its basic protocol, and how to apply, that you have to understand, and your material science and its knowledge. So these all are key fundamentals which you have to understand. So let me brief it, and the number one will be your, I think, is about material science, and number two will be about your strength of material, and number three will be your machine design. So these are the three important aspects, and also you need to master your drawing concept, and this is one of the four different pillars which you can say about your prerequisites, and you have to understand this. And let us look at the sample course preview, and here we are talking about FEA Kickstart concept mastery, and we'll talk about understand the basic concept and general working of finite element analysis, understand the advantage and also the disadvantages of finite element analysis. We'll understand different types of analysis as well, and we'll look into important terms and definitions in finite element analysis. These are our sample course learning objectives, and we'll look into these four different concepts. So when we talk about finite element analysis, it is nothing but an approximation method, or you can say a particular technique which you use to obtain very close mathematical solutions by assigning the assumptions or the load data. And the numerical method is nothing but is called globally as finite element method. To better understand this particular concept, I will introduce you with this particular circle. And if you see this circle periphery, and let us say this is my center, and here you have your radius protocol. And how can you find the length of the circle or periphery of the circle, or the periphery you can say, or the stretch length of the circle? How can you find out? Or you can say you know the formula, and that is nothing but 2 pi and r. But you may be wondering how this value of pi we can interpret. I know the value of radius. I can measure from here to here and get the radius data. I can measure it. The distance protocol I know. But what about this pi? So if you think this in a different way, So let us say this is your circle and you divide this into four parts, let us say. And in finite element, there is no definition of any curvilinear part. That means you connect here to here in a straight line, here to here in a straight line, and so on. Then you measure what is this particular length. Let us say this is x dash and this is x double dash and so on. So what you do is collectively x dash plus x double dash plus x triple dash plus this equal to your length of your circle, length of your circle. So this length plus this length plus this length plus this length. And here you incur the errors because you omit the curvilinear part. And take another case where this particular circle you are going to divide not by four parts but like your clock maybe in 12 parts. And you are very close to a straight line here, you can see. You are very close to a straight line. And this delta x whatever you have, so 12 into delta x is nothing but length of the circle. And think about a case when you can increase this particular patch. I can show you here clearly. This is the one patch where I am dividing this very closely. When you divide this very closely, what happens is you are very close to the straight line part. And even though that curvilinear part is very close as straight line. And this is the typical technique which you use in finite element. And by using that, you can directly find your pi. So how to find the value of pi? That I will show you. And also you can see the typical different options where we can configure that and we can find the data as well. So let me show you this particular pi value calculations, how you can do that. And by understanding this, you directly can correlate that. So let me show you. And as by knowing the formula, you know the 2 pi r is nothing but equal to your periphery of circle. And what you can do is pi is nothing but is periphery of circle divided by 2 into r. So whatever the periphery of circle here I told, let us say you divided by 12. So this periphery of circle is nothing but 12 into delta x divided by 2 into radius. So radius you can measure directly from here, or whatever the radius here you have, that you can directly measure. And this radius value you put it here, and this delta x values, whatever the delta x you talk about, this delta x you can get it here and you get. So let us assume instead of 12 you are dividing that into 100 parts, or maybe 1000 parts, or maybe 10,000 parts, or maybe more than that, a multiple of that. When you divide, you approach very close to your circle's periphery. And here, whatever the error you have, like this, or maybe if you connect it, this is the error which you get, and that you can reduce gradually when you keep on going. So the more the numbers, that is a technique typically we use in finite element. That is known as the particular, you can say the meshing method, which we use under this particular technique. So how to interpret that? That is our agenda here. That the typical methods or mathematical way which you use. And here you can see to the get the accurate value of the perimeter, divide the circle into more segments. That is what the understanding. The FA was first developed to be used in aerospace and the nuclear industries, and these are the two benchmark, or you can say the application industry, where they improved and optimized the data gradually. And today even the simplest of the product rely on FEA for design evaluation, and the FEA simulates the loading condition, which is very important of your design, and determines the design response in those conditions. That means you have your system, this is your system, and here you load your data. That data may be your material, that may be loads, and that may be your object. That object is your model or the geometry or your product, and you get as the byproduct response. So system, the input, the data is nothing but, you can simply say input. When you input your data like the material, loads and object, or typically you can say all the conditions, boundary conditions, your the design data, and your system is nothing but the finite element analysis technique, which is your post processor, and based on that you get your response. And to better understand this, a spring assembly that represents a simple two-way spring element model like the one is shown here, and this particular end is fixed, and here in this particular direction the load is applied. And by seeing this, what we used to understand is, suppose let us say I will just do that in this way, spring system, and there is a mass W, and this particular spring having its stiffness, and that stiffness is known as K, and applied load whatever the F gives you the response, that is the deflection of the system. So by using that, it is evident that force is nothing but the stiffness and factorization of your distance or the deflections or whatever you talk about. So this two factorization is nothing but F equal to K into X. K is the stiffness, and this, so this is the force exerted, and K is the spring constant, that is the stiffness, and X is the deformation. And for the given particular spring, as multiple springs with different stiffness, like K1 stiffness and K2 stiffness, others are there, like this is basically one particular area where your stiffness factor is something this. And when you talk about this, so this particular area where you talk about the different stiffness, that factorization you can do, like the response x1 is different for the k stiffness, and this response for this is different because x2 minus x1 is the net distance, and that typical distance into k2. And by using this particular case, you can get the f1, because based on the f1 how the response is, and based on the f2 how the response is, that you can compute. And typical the deflection here, and typical deflection here for this case, you can collectively compute. And if you have a complex architecture other than this, so if you talk about any products, maybe you talk about your typical steering suspension system, you talk about your chassis, you talk about your axle, then there you have this particular systems interpreted complex architecture where this particular formula sits, and that is the background of your finite element analysis. And this all format, like two different forces are inputted, and the right side you can see the k factorization and your deflection factorization, that is arranged in matrix format, and those independent evaluations are interpreted for each and every element. That is basically the circle example you saw. When you divide this, each are known as one element. This piece is known as element, and finally you assemble this and get this result. And the element shape is determined by nodes, and these connected points are nothing but your nodes. These connected points, these are your nodes. So let us talk about a particular block. Maybe this is the simplest example which I can show you. And when you divide this, maybe this direction by 4 and this direction by 4, and this small piece is your element 1, and this piece your element 2, this is your element 3, and this piece is element 4, and so on. This backside and another 4 elements. So this collectively, all these elements are connected at these points, and these points are nothing but your nodes. And the more accurate your result will be, in the more accurately how you divide that or discretize that. So let us talk about a particular shaft where you have curvature involved. You can divide this length area into these pieces, but when you divide this periphery, there you divide this periphery as well, and then you connect, and these are the elements, and there let us say you have applied a particular load here, or maybe a axial load here, load 2, and this is your load 1, and let us say this end is fixed, and you need to see the response, whatever the response you have, and maybe at this particular point you need to see the response. All this is only possible because of elemental and nodal relationship. And this is the discretize, the case where you can see the node and element structure in a simple geometry like this triangular shape and the truss-like shape. And elements are of different types, maybe the line element. If you can discretize a typical problem into a line element, let us say you have a shaft, and this shaft having its typical diameter, and if you can represent with a line element and attach the area of cross section as whatever the value here you have, that also is one of the important aspect in finite element. So what you can do is you can simplify your project with line element, and you can attach this as a area of cross section, and then whatever the load data you have like P2 and P1 and so on, and you can get the response based on that typical factors at different points. So the element shape is very important, and like the straight line, if you have a complex shape, you have a quadratic element where you can also have a deflections, and this can represent a twist and kind of, you can say, stiffness. Let us say this is the line element, and if it is quadratic type, it can actuate like this, just like a suspension system. And if it is rigid, and it directly can move in a straight line. So if you are interested for this kind, you can also configure the type of response or type of behavior for this particular element, and that we'll discuss in fact in our coming session in brief. And this again, when you talk about the line element, then next type we move to the area element. When you represent areas, again it is having a 4 noded element, and if it is having higher stiffness or stretchability, then you can introduce 8 noded element, or you can have the triangular element, or you can have a second order triangular where you have middle nodes, and which can give just like a filling of this type if it is not rigid or straight line. Just like that for the volume element, or you can say the 3D element is again started with a brick shape, then you go for the quadratic type where you have middle nodes which can behave like your curvilinear, and then you have like the wedge, and again wedge shapes second order, which is again of another type. These all types you have to understand and use it, and it's very important to understand the procedure to conduct finite element analysis. The first of all, you have to understand which analysis you are going to conduct. Then how do you know it? So maybe you talk about a particular product that is a piston, and piston's response you need to see during the combustion, and how the typical thrust is transferred to your connecting rod, and then to your crankshaft, and then to your flywheel, then to your complete clutch system, and then to your road wheels through propeller shaft. And you need to understand the response. So first of all, you need to understand your structural stability. What about all the forces acting in your piston? And by understanding that, then you can go for the dynamic response. Then you can see the modal response like natural frequencies. Then you can see the impact and so on. And then you will go for the thermal analysis. Then you will see the combined effect of thermal and structural, that is known as coupled field, and so on. So first of all, you need to understand your motive or the end result, the analysis to be used. Then you have to go for a create model. Maybe directly your modelers directly give you a connecting rod, and there you have very small fillets, small holes that you may ignore in your finite element analysis in order to understand the mathematical aspect. The small holes or the fine curvature or the fillets are not important as a part of understanding mathematically. So you have to define the model very specific for finite element analysis. This is the most important part where most of the people to miss it. And then you define the element type, which I discussed, like the line type. Can you represent a connecting rod in line type? Of course not, because it's complex. You have to go for a 3D model. Can we represent a particular example where we can derive a line type? Absolutely yes. So maybe your typical Excel for understanding, you can start with a line type model and understand the spring behavior where the differential is loaded, where the wheels are loaded, and 3-point actuation. And then you can understand the road thrust and then the load transfer from the vehicle to your ground. And so all the contact points can be numerically derived as a single line, and it will act like your spring. And you can understand it. Then you can go for your 3D model and again refine it and go for the next level, and then divide the given geometry, that is the model which you have done, and after selecting the element you divide it, because our approach always is to get the closest possible mesh model where you are very close to the physical model, that deriving a mathematical closed physical model for solution. And then we apply the material properties, apply the boundary condition. Boundary conditions means, let us say you talk about your axle. Axle is mounted where? That is your boundary condition. Differential is loaded where? That is your axle boundary condition as well. And what about the wheel? Wheel is mounted in your axle, and wheel also is in contact with your ground. There you have a friction, that is a boundary condition. And wheel is mounted in your complete mechanism, and that it can actuate during your steering. So you have a degree of freedom. That degree of freedom is your boundary condition. So we'll brief more about this boundary condition in our coming chapters and lecture and material selection as well. But in order to just give you one insight and give you the understanding about how to apply this boundary condition, just I briefed, and then derive the element matrix and equation, which type of equations you are going to select, a linear element or nonlinear, or maybe hyperelastic or elastic or viscoelastic, and so on, and set a particular equation for solving that. And then finally we'll assemble the elements which I was discussing, that independently will calculate at each element level. Let us say this is my physical model, and this is the element 1, and this is your element 2, element 3, and element 4. The first of all, we'll calculate each element's result, then we'll assemble this result to get the response of this whole system or your physical product, and then solve the unknowns, which are unknown, that we'll be finding out, and then we'll interpret the result, evaluate the result, and then we'll get the final, you can say, the outcome. The FEA through software involves typically three steps. Pre-processing. Pre-processing is nothing but assigning the material property, assigning the boundary condition, assigning the loads, and to whom? To your model. Is all are known as pre-processing. And one important aspect is meshing. And these five things, like the material, boundary condition, load data, meshing, and your model, that is your 3D model, 2D model, or whatever model you have. These all five operations are coming under pre-processing. And solution is type of analysis, type of results you are looking for, and selection of your post-processing method, and that is nothing but your equations, And finally, the post processing is result. You will get the answer through this. So this is the very simple architecture where you create your physical model, then you generate your nodes, elements, boundary condition, material properties, loads, and other conditions. That is the pre-processing which I was discussing. And in solution page, you will generate the element matrix or the mathematical procedure and compute the nodal values and derivatives and store the result. And post-processing is to view the result, analyze the result, display the data like the graphs, plots, results, node result, element result, whole projects, physical result, and these are the stages of finite element analysis. And different FEA softwares, commercial softwares, and educational softwares are available, and that you can see like ANSYS, Abacus, Adina, NISA, PEMCRAS, Altair products, and so on. Bunch of products you have. And primary advantages you have to understand before going through the limitations. So each package having their limitation, but before discussing this limitation, I would like to highlight the this broad advantages. It reduces the amount of prototype testing that I was discussing in my very first lecture session, thereby saving cost and time. It gives the graphical representation of the result of the finite element modeling and analysis which are performed in the preprocessor and solution page, which is done manually, would consume a lot of time, like hand calculation you do, and in some cases might be impossible to perform, like the complex architecture of an aircraft, a complex architecture of your automobile system. You just imagine, and how do you integrate everything and not only interpret about the structural stability but dynamics. Again, you have the crash analysis, you have your different conditions like your road shock and bump, and various other 50 to 100 types of analysis you perform. And variables such as stresses and temperature can be measured at any desired point of time and any particular point of your model, and it helps optimize your design. This is a very important aspect, and it used to simulate the design that are not suitable for prototype testing as well, and it helps you create more reliable, high quality, and competitive design than your competitors. And these are the primary protocol advantages, and some limitations as well we have. It does not provide exact solution. You have to understand, mostly this is exaggerated, and you have to understand this. What is the it does not provide exact solution? As I was discussing about your circle example, if you divide this into four parts, of course it will not give you the exact answer. But for dividing this more closely, you need more capable systems like workstations, which can give you more close results. So the meshing is the primary protocol. Selection of the methods are the primary protocol. There we do mistake. And instead of solving the project, you go to your site, investigate and understand the more and more inputs. And if you can spend more time, you will get more close result. So that is the meaning here. Is meaning not exactly what it is written. It does not provide exact solution. And API packages are costly. This of course is one of the limitation. Everybody cannot afford finite element analysis package, and some of the software like deform 3D in Indian currencies, and that is 2 CR, 2 crores, and the ANSYS package also in commercial version also is very costly, and Altair also is very costly. So you have to understand that. An inexperienced user can deliver incorrect answer. This is of course, and upon which the expensive decision will be completely scrapped, and who will be responsible. So you have to be experienced to understand and use this package. And results give solutions but not remedies. So this is one of the important aspects. Results give solutions but not remedies. If existing system you have to improvise or you have to upgrade, then you have to completely use these solutions to get the answer, but it cannot remove your remedies. And features such as bolt, welded joints, and so on cannot be accommodated to a model, and this may lead to approximation and errors in the result. And this also is not true. The solutions like ANSYS Workbench There you have the protocol, how to apply the welding joints, bolts, and all. But as far as the ANSYS mechanical and other license are concerned, there primarily also you have solutions like you can attach the bolts properties instead of directly modeling that, but directly mostly the basic beginner user, they cannot use this particular aspect, so that is a limitation for us. For advanced user, this is not a problem at all. For more accurate result, more hard disk space that I was discussing, and more RAM and timer required. That means more costly system you need to purchase. So these are the limitations, but primarily I don't think as an advanced user I can have all the problem solution. But still, for the basic user, beginners, these are the limitations that you have to keep in your mind. And if you are using your office desktop where you have maybe 16 GB of RAM, these are not enough. And currently the system which I'm using for recording this having 128 GB of RAM and more than 20 GB of professional graphics and having a Xeon processor which is very costly, and this also most people cannot afford. So that you have to understand very clearly. And key assumption in finite element is very important that can directly result your solution's accuracy. So four type of key assumptions that we consider while performing finite element analysis. The assumptions related to geometry. This geometry is nothing but your modeling. As I was discussing, if you talk about a connecting rod, exactly modeled connecting rod is not the input for your finite element analysis. You have to remove the small holes, you have to remove multiple fillets or sharp corners, and you have to simplify that for your finite elements. So displacement values will be small so that linear solutions is valid. Stress behavior outside the area of interest is not important. Therefore, geometric simplification in those areas do not affect the outcome that we do, that I was discussing. And only internal fillets in the area of the interest will be included in the solution. Local behavior at the corner, joints, and intersection of the geometry is of primary interest. Therefore, no special modeling of this area is required. So, sometime you can derive a very simplified model of your complex model, and decorative external features will be assumed insignificant, so that will be removed. Let us say you apply one fillet for aesthetic look, that is not important for our design consideration, please remove that. And that insignificant for the stiffness and performance of the part, and this external feature will be omitted from the model, and variation in the mass due to suppressed feature is negligible, and this is very important. And whatever the suppressed features you do, maybe that is coming around 50 grams as compared to your parts weight of 3.5 kg, that you can ignore. So this is not going to drastically give, maybe 0.5 to 1% error comes, but that is okay. And assumption related to material property, this is very important. Material property will remain in the linear region, and the nonlinear behavior of the material property cannot be accepted. And even this is not true, nonlinear material also you can model, but primarily the assumption for simplified projects, we go for a homogeneous material, or you can say a linear material. And material properties are not affected by the load rate, and the component is free from surface imperfection that can produce stress concentration. All simulation will assume room temperature, ambient temperature, unless otherwise specified. And these are the some assumptions, but this is not the thumb rule. In most of the cases, we use this, and nonlinear materials all it supports. But still, we start with a linear material. The effect of relative humidity or water absorption on the material used will be neglected, and no compensation will be made to account for the effect of chemicals, corrosive, wear, and other factors. Even we have specific analysis related to wear or corrosive, or maybe the particular advanced features. So these are the two different assumptions. The third assumption is related to boundary condition. This is very important. Displacement will be small so that the magnitude, orientation, and distribution of the load remains constant throughout the process. That means you assume a elastic proportional limit. That is true only for the basic model, but still ANSYS is capable to perform inelastic or hyperelastic or viscoelastic advanced options. So for that you need to have that particular knowledge and basic understanding. But in most of the cases we begin with this basic assumption, and friction loss in the system is considered to be negligible, and all interfacing component will be assumed, and the proportion of the structure being studied is assumed as a separate part from the rest of the system, so that any reaction or input from adjacent feature is neglected. In most cases you can interact, like you talk about a gudgeon pin where this is connected between connecting rod and your piston, where the interaction of the piston and your connecting rod, when you only model the gudgeon pin, can be taken as input, but the corresponding reactions how that will be over the piston is not considered. We are only interested to look at the gudgeon pin. Or maybe you talk about a connecting rod, and that is one end connected to your gudgeon pin through your piston and another end is to the crankshaft, and there you are primarily not focused at the crankshaft interaction in the piston. You are looking at how the connecting rod, because you are looking at connecting rod design. So that is what the assumption is all about. And last important aspect is assumption related to fasteners that I was talking about. So when you talk about the fasteners, we have the provision, but still the residual stresses due to fabrication, preloading on bolts, welding, or other manufacturing assembly process will be neglected. But still, we have a process where we can consider this, and all welds between the component will be considered as ideal and continuous. That means it will act like your rigid part. But still, we have a provision to interpret and understand weldings. The failure of fastener will not be considered. This again for the beginners and related to the simple project. And the load on the threaded portion of the part is supposed to be evenly distributed among the engaged threads. And the stiffness of bearings both in radial and axial direction will be considered as infinite and rigid. These all are assumptions. And let us understand type of engineering analysis, which is very important. And to start with, we'll understand the structural analysis. And the structural analysis has also various subtypes. So let us start with the static analysis. As the name static, you can understand the structures are in the equilibrium condition and you try to understand. Then dynamic analysis, and also you have spectrum related to earthquake, buckling, and explicit dynamic analysis. And again, this dynamic is subdivided into modal for the response related to natural frequency, harmonic, the f sine omega t aspect, and transient related to time. When the effects are different, then you can go for the transient. These are the type of structural analysis, and structural analysis are broadly classified in this type, and dynamics also part of structural analysis. And then again another type is thermal analysis, and this particular thermal analysis is very important to interpret and understand the task related to thermal quantities such as thermal distribution, amount of heat loss or gain, thermal gradients, and thermal process that we'll be looking in our coming session in brief. And again, thermal divided into two different types: your steady state, where the system is studied under steady condition and that time equal to constant, and in case of a transient condition, the system is studied under transient condition. That means where the time is not constant. And another important aspect of the analysis protocol is fluid flow analysis. There you talk about the fluid's behavior and temperature and the typical distribution flow, where you talk about the velocities, pressures, temperature, and the film coefficients and its interactions. And also you have the electromagnetic analysis, and that is very advanced and important nowadays, and to understand the magnetic fields in electromagnetic devices. And the final very important, my favorite, is coupled field analysis. Here you basically understand interaction between two or more fields. For example, the fluid aspect with thermal, or structural aspect with thermal, and so on. And this is one of the advanced aspect. Let us talk about the deliverables which you will get from this course. And the deliverables are the all modules soft copy files, assembly files, drawing files where applicable, and lifetime support related to technical doubts through our forum support, 24 by 7 at the rate smartlearningindia.com, and you can also directly go for info at the rate smartlearningindia.com to get 24 by 7 lifetime support and drawing PDF copy for your easy reference, and tips and tricks session with all the modules for increasing productivity and advanced industrial approach, and all modules video license also will be given to you. Thank you for giving your time, and I appreciate you all.